Let's start by substituting 20 milliseconds into the voltage across the capacitor expression Vc of t. This yields a value of roughly 11.2 volts. We could substitute t equals 20 milliseconds into the other time-varying expressions. However, we could also use much simpler, more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Given an 11.2 volt differential across the capacitor, this means 24 minus 11.2, or the remaining 12.8 volts, must necessarily appear across the 500 ohm resistor. Quick application of Ohm's law demonstrates that with 12.8 volts across a 500 ohm resistor, approximately 25.6 milliamperes must be flowing through it, and by extension, 25.6 milliamperes must also be flowing into the capacitor because they are in series with one another. In summary, at t equals 20 milliseconds, Vc equals 11.2 volts, Vr1 equals 12.8 volts, and both IR1 and IC equal 25.6 milliamperes. For our second example, we know the instantaneous voltage across the capacitor Vc to be 0 volts. Therefore, 24 volts minus 0 volts, or the remaining 24 volts, must appear across the resistor 1. With 24 volts across a 500 ohm resistor, Ohm's law demonstrates that current through it, and by extension through the capacitor, must equal 24 volts divided by 500 ohms, or 48 milliamperes. In summary, Vc equals 0 volts, Vr1 equals 24 volts, and both IR1 and IC equal 48 milliamperes. Importantly, when does this event occur? We could use any of these expressions to solve for the time value that satisfies any of these conditions because they all happen simultaneously. Let's just use the expression for Vc of t. 0 volts equals 24 volts minus 30 volts times e to the negative t over 23.5 milliseconds. What time value satisfies this condition? Subtract 24 volts from both sides. Divide both sides by negative 30 volts. Take the natural log of both sides. Get rid of the negative sides on both sides and multiply both sides by the time constant. We're left with a time value of roughly 5.2 milliseconds. Moving on, consider this challenge scenario building upon the charging circuit we examined in example 3 during the capacitor charging lecture. You'll recall, example 3 was a series circuit consisting of an 8 volt source, a switch that closes at time t equals 0, a 250 ohm resistor, and a 2 microfarad capacitor. During the charging process, we learned at a relatively short time constant of 500 microseconds, or 0.5 milliseconds. When Vi initial voltage of this capacitor was assumed to be 0 volts, we observed the following properties. Current through the capacitor as a function of time, IC of t, during the charging process was 32 milliamperes times e to the negative t over 500 microseconds. Current through the capacitor experienced an initial surge of 32 milliamperes and decayed to 0 over 5 time constants, or 2.5 milliseconds. Voltage across the capacitor Vc of t during the charging process was 8 volts times 1 minus e to the negative t over 500 microseconds. Voltage across the capacitor started out at 0 volts and grew to 8 volts over 5 time constants, or 2.5 milliseconds. Current through resistor 1 as a function of time, IR1 of t during the charging process, also equaled 32 milliamperes times e to the negative t over 500 microseconds. Current through resistor 1 and all elements in series with it experiences an initial surge of 32 milliamperes and decays to 0 over 5 time constants, or 2.5 milliseconds. Finally, Vr1 of t during the charging process was 8 volts times e to the negative t over 500 microseconds. Voltage across resistor 1 surged to 8 volts and decayed to 0 over 5 time constants, or 2.5 milliseconds. You'll note voltage for the circuit never exceeded 8 volts. If left to its own devices, the final voltage for the circuit would always result in an 8 volt differential being applied across the fully charged capacitor after the passage of 5 time constants, in this case 2.5 milliseconds. For the purposes of today's lecture, let's assume the capacitor initiates the charging process not at 0 volts, but rather with some start voltage Vi of 10 volts, oriented positive to negative, top to bottom. Yes, you heard me correctly. Positive 10 volts. i.e. an initial value greater than what we'd ordinarily expect for a final value with this charging circuit. Yes, this is a little different from our previous examples, but it's well within your capacity to understand how the system works with a little thought and investigation. You'll note, despite the incorporation of an unexpected initial condition, the time constant for the circuit remains the same at 500 microseconds. Let's make this an interactive exercise. My first question to you is this. What happens during this quote-unquote charge phase when the switch closes at time t equals 0? Here's a hint. Consider instrumentation placed in the following fashion. Voltmeter C reads the voltage across the capacitor positive to negative, top to bottom. Ammeter C reads the current through the capacitor in to out, top to bottom. Voltmeter R1 reads the voltage across the resistor positive to negative, left to right. Finally, ammeter R1 reads the current through the resistor in to out, left to right. What happens when the switch closes at time t equals 0? Importantly, which direction does current flow through the system, and with what polarity does voltage appear? Finally, is it really appropriate to call this a capacitor charging circuit? Here's a hint. The superposition theorem may help you out. By all means, pause the lecture and think about this. If you're tracking, you should have arrived at the following conclusions. Bottom line up front, this is not a capacitor charging circuit, but rather it's a capacitor discharging circuit. However, instead of completely discharging the capacitor to 0 volts, it only discharges it to 8 volts. If you want to think of it this way, this capacitor is initially overcharged to 10 volts, and this circuit will bring it back to 8 volts. As long as you keep track of signs, all of our previous analysis techniques hold true. Allow me to demonstrate. At t equals 0, one end of the 250 ohm resistor is at 8 volts, and the other end is at 10 volts. At t equals 0, this resistor therefore experiences a differential of 2 volts, only it's oriented positive to negative, right to left. Kirchhoff's voltage law supports this conclusion, where E equals VR1 plus Vc. Substituting in our given values, we find VR1 to be negative 2 volts. As a result, current will travel out of the capacitor, into the resistor right to left, and through the source top to bottom. Thus, current for both the resistor and capacitor will have an assumed negative direction. Ohm's law demonstrates with negative 2 volts across a 250 ohm resistor yields an initial current surge of negative 8 milliamperes, where the negative sign is indicative that current is traveling right to left. The superposition theorem supports this conclusion. At t equals 0, the 8 volt source and the 10 volt capacitor oppose one another. When these effects are superimposed upon one another, accounting for polarity, the resistor experiences a differential of 2 volts, positive to negative, right to left. The capacitor will discharge through the resistor and into the 8 volt source. Voltage across the capacitor as a function of time Vc of t can still be expressed as Vf plus Vi minus Vf times e to the negative t over tau, where Vi is the initial voltage of 10 volts and Vf is the final steady state value of 8 volts. Substituting these given values, Vc of t resolves itself into a simplified expression as 8 volts plus 2 volts times e to the negative t over 500 microseconds. Voltage starts out at 10 volts and eventually stabilizes at 8 volts over 5 time constants or 2.5 milliseconds. As long as you keep track of signs, this expression will work for any scenario. Current through the capacitor as a function of time, Ic of t, can be expressed as negative 8 milliamperes times e to the negative t over 500 microseconds. Current experiences an initial surge of negative 8 milliamperes and decays to 0 by 2.5 milliseconds. Because the resistor and capacitor are in series with one another, current through resistor 1 as a function of time is equal to Ic of t. As such, IR1 of t can also be expressed as negative 8 milliamperes times e to the negative t over 500 microseconds. Finally, voltage across the resistor as a function of time VR1 of t can be best expressed using Ohm's law, as VR1 of t equals IR1 of t times the constant resistor value R1. Substituting in these given values, VR1 of t resolves itself into negative 2 volts times e to the negative t over 500 microseconds. R1 again experiences an initial differential of 8 volts minus 10 volts, or minus 2 volts, which then decays to 0 volts by 2.5 milliseconds. You'll note at 2.5 milliseconds, voltage on both sides of the resistor would be 8 volts, and the voltage differential across it is 8 volts minus 8 volts, or 0 volts, thus explaining the eventual halt of current, given a differential across it no longer exists. Is this an odd example? Yes it is. However, all of our previous analysis techniques remain valid and illustrated an important property of capacitors. Notably, capacitors resist sudden changes in voltage. In all of our examples, including those that had positive initial voltages, negative initial voltages, and even excess initial voltages, the voltage across the capacitor never underwent a disjointed instantaneous transition or a sudden reversal in polarity. That's the point. Capacitors resist sudden changes in voltage and are often employed in circuits that necessitate relatively steady or slowly changing voltage conditions. Also, it may be helpful to remind ourselves how the charge and discharge processes unfold. During a charging process, current rushes through a resistor and into a capacitor, while charging voltage across a capacitor rises. During a discharge process, current rushes out of the capacitor and through a resistor. While discharging, voltage across the capacitor drops. Any voltage experienced by a resistor is simply a consequence of the incoming and outgoing current experienced by the capacitor during the charge or discharge process. As a remaining exercise to the viewer, I invite you to solve for the instantaneous voltage across the capacitor, current through the capacitor, voltage across the resistor, and current through the resistor at time t equals 600 microseconds. Additionally, see if you can determine what time the capacitor reaches 9.5 volts. At this time, see if you can determine the instantaneous current through the capacitor, the voltage across the resistor, and the current through the resistor. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following values. For our first illustrated example, substitute 600 microseconds into the voltage across the capacitor expression Vc of t. This yields a value of roughly 8.6 volts. We could substitute t equals 600 microseconds into the other expressions. However, we can also use much simpler and more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Kirchhoff's voltage law demonstrates that with an 8.6 volt differential across the capacitor and an 8 volt differential across the source, the resistor will experience a negative 0.6 volt differential, where the negative sign indicates current will be traveling from the capacitor through the source. A quick application of Ohm's law demonstrates that with negative 0.6 volt differential across a 250 ohm resistor, approximately negative 2.4 milliamperes must be flowing through it, and by extension 2.4 milliamperes must also be flowing out of the capacitor because they are in series with one another. Again, the negative sign indicates that current is traveling from the capacitor through the resistor right to left and into the source. For our second example, we know that Vc equals 9.5 volts. Therefore, R1 must experience 8 minus 9.5, or negative 1.5 volts must appear across the resistor. With negative 1.5 volts across a 250 ohm resistor, current through it, and by extension through the capacitor, must equal negative 1.5 volts divided by 250 ohms, or negative 6 milliamperes. In summary, when Vc equals 9.5 volts, Vr must equal negative 1.5 volts. Both IR and IC will equal negative 6 milliamperes. Note all these events occur simultaneously. The remaining question being, at what time does this event occur? We could use any of these expressions to solve for the time value that satisfies any of these conditions because they all happen simultaneously. Let's make our job simple and just pick an easy one like VR1 of t. Ultimately, we're left with a time value of roughly 143.8 microseconds. Alright, that's about it for today. We'll examine capacitor partial charge and partial discharge scenarios in later lectures. In conclusion, we examine the capacitor charging process, including initial conditions. We learned initial conditions merely change the starting point for voltage across the capacitor as a function of time. The resultant differential at the start of the process determines the initial magnitude of current. Regardless, the process unfolds within 5 time constants. Additionally, we kept our instantaneous analysis skills fresh with a couple illustrated example problems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.